Welcome back. So far, what we have seen that how to define the space, and if I have a space, then how to define some kind of binary operation inside that space. Okay, and with help of that binary operations like vector addition or scalar multiplications, what we found that I have come up with some concrete notion that is vector space, and that is also called linear space. Okay, and after that, what we found that we have concept of the linear combination, basis, span, dimension. These kind of things we have explored in the previous class. Okay, and using help of that, what we found that at least whenever I have some kind of algebraic equation, in previous class we have seen that I have some kind of LTI system, linear time invariant autonomous system, then I can able to also talk that under what condition we have unique solution, or in more generalized case, if I have some kind of algebraic equation in this form, then under what condition I can tell that there exists a unique solution or not. Okay, so if you see the vector space carefully, then they have given several beautiful concepts. Okay, concept like linear combination, concept like subspace, basis, dimension, and these kind of things are pretty much useful whenever we are dealing with the system. But one notion that is still missing in case of linear space, if you just limit yourself on the vector space, that I cannot able to define the nearness, okay, or proximity. That suppose I have two vectors inside some space, so how to tell that vector, or suppose you can three vectors in place of two vectors, then how to tell that first vector is closer to second vector. Okay, when I cannot able to distinguish between two vectors, so that kind of notion is not available in case of the linear space or vector space. Okay, and due to that reason, now what we are going to do, we are going to add some more notion inside the vector space. So all property of vector space is going to preserve. Okay, but on top of that, I want to add one more flavor such that I can able to define the property of nearness or property of proximity. Okay, why and why that is very important? Because somehow I have to talk about the convergence. Okay, you might have seen that whenever we are talking about some kind of linear system, at that time we are talking about if I have some kind of LTI system or LTV system, if I will give the bounded input, then what kind of response I will get? Anyone, could you please tell me? For linear system, and suppose this is a stable linear system, and if input is bounded, then what kind of behavior I will get?
Bounded output, sir.
Bounded output. So this kind of behavior. So now we are telling bounded input and bounded output. So first important point, how to define bounded input and bounded output. Okay, so in vector space I don't have such kind of notion such that I can define the boundedness. Suppose now if input is converging towards the zero, then I expect that if system is stable, then output also converges towards zero. But that kind of notion I don't have inside the vector space, and due to that reason, in order to add notion of the convergence or limit, you can tell, or notion of continuity, these kind of concept in higher dimensional space, I need one more notion that is called norm. And it is possible to show that norm is nothing but the generalization of distance. Okay, so whenever I am talking about distance, what is beauty of distance? That I am able to do comparison. Okay, so suppose if I will ask one question that I have 1 and 2 and 2 and 3. Okay, I have two vector in two dimensional space, So is it possible to tell that this is A1 and A2, A1 is greater than A2 or A2 is greater than A1? Is it possible to talk? Anyone?
No, sir.
It is not possible to talk. Okay, so I cannot able to do comparison in higher dimensional space. So thing is that now I have to find some kind of way to compare it, and it is possible to show that I can only able to compare in one dimension. Most of time there are some generalization, but most of time in one dimension I can compare, because whenever we are talking about one dimension, at that time every quantity in some real line, so I can exactly know that if some quantity here and some quantity is here, then in terms of distance, or even if that is here, that doesn't matter, because whenever we are talking about distance we are talking about positive number. So by looking towards distance I can compare the two quantity. So what is main motivation? Whenever we are talking about norm in higher dimensional space or vector space anywhere, then first important point, I have to map this two dimension to one dimension, and I have distance kind of quantity, so that is always positive. Okay, and during school time you might have seen that whenever I have point in two dimensional space x1 and y1, how to define distance from here to here? Could you please quickly tell me?
Root over x1 square by
X1
plus
square
y1
plus
square.
y1 square. You can see now two dimensional quantity I have just mapped to one dimensional quantity by one dimensional quantity by defining this kind of relation. So now since we are become more mature, so we are going to see that this is only way to define distance, or we have some other way. Okay, or in another way you can take one practical problem. Suppose you have to move, suppose this is point A, this is your city, and I have something like this, and I have to go from A to C. If do not exist some direct path between A to C, could you please tell me the solution how to move from A to C, or how to give some kind of polar taxi to give instruction that I
AB
can move from?
vector plus BC vector.
So I have to move from here to here, and after that I have to move from here to here. Okay, so I cannot able to define distance in this way. I have to define distance like now at that time x1 and y1 like that. Okay, so distance now I have to define something like that, then only I can able to reach from here to here, because there is no path available from here to here. If I will calculate that distance, that is not the exact distance, and due to that reason I need some more way to define the distance. Okay, and obviously a space whatever I am going to consider, that is vector space, linear space, and due to that reason name that comes into picture, that is called non-linear space. So this is the story. So let us start the story. So now here I have already told you that whenever we are going to define the norm linear space, at that time I have now some kind of ordered pair. Ordered pair is that vector space, and after that I have some notion of the norm. Okay, so norm linear space is some kind of ordered pair where property of this particular operator, that is called the norm. So if you put any vector from this space to this operator, then that map to some kind of r plus, some kind of positive real number. That is the property. Okay, so same kind of things I have written. A non-linear vector space is vector space X on which there is a defined a real valued function. What is real valued function? Means if you take any element from this space, now you can, I have already told you that a space may contain column vectors, may contain functions, or some kind of matrices. So if I will apply, if I will take any specific element from this space and keep here, then finally I will get some kind of positive number, and that positive number is some kind of real number. So this particular operator is mapped to some kind of real valued function. Okay, and so same kind of things I have written, and for that we are going to use this notion is nothing, I am giving some specific name norm, and you can see that norm is the abstraction of usual concept of length. What I am telling, suppose you have to define the distance, this is your origin, so either point is lying here and lying here, so sign doesn't matter for us. So due to that reason distance is always positive, and first thing is telling that if you take any element from the vector space, and if you put inside this symbol, then that is always greater than equal to 0, and 0 is only allowed if you are at the reference point. It means that if that is 0, then I can tell that x equal to 0, or that vector is 0, or in that way also, means both way I can tell that x equal to 0, then norm x is 0, or norm x is 0 means x equal to 0. After that, you can see that triangular inequality will satisfy. So suppose that now I have already told you that if I have to move from here to here, and if you start moving from here to here, then this inequality will satisfy. Okay, and scaling, if so, now whenever we are defining some kind of vector space, you might have seen that I am taking help of field. So if you involve the field element here, and most of time in our purpose I am assuming that field is real number, or for analysis purpose complex number we are using, if we are talking about classical control. So suppose that if I limit for the real number for the modern control theory, then you can see that this alpha is real number. So if you scale out, then this kind of relation will satisfy. So it means that if you move from more point, means if you scale each some vector by alpha amount, then what happens that distance is also scaled by same amount. That is the meaning. Okay, so this is just abstraction of the distance. Now you can take element, and now you can define function, norm function, such that if this property will satisfy, these three property will satisfy, then I will tell that that particular way is correct way to define the norm. Okay, now one simple question I am going to ask, and that is obvious also. Could you please tell me that how many different way now I can define the norm? Anyone? Have you understood my question or not? I am telling that norm should satisfy these three properties. Okay, so how many different way I can define the norm? Unique or non-unique? Manali, could you please quickly answer?
So it's non-unique only, sir.
Non-unique. Okay, I have infinite many choice now, because just I am telling that each choice should satisfy this, and due to that reason I have infinite many norm. Okay, that is the beauty. Okay, let us come to the some example. Now first example, we have already proved that if I have some kind of continuous function in some interval a and b. Okay, so continuous function forms some kind of linear space. Why linear space? If I will define addition pointwise addition, or multiplication by the point by multiplication. Okay, now what I am going to do, I am going to add the notion of distance, and you can see that I have added notion of distance in this way. What I am telling, if I have some kind of continuous function between a to b, then I will take the absolute value between a to b. Okay, and what I am going to do, I am going to just select the maximum one. Okay, so in another way, suppose you are looking towards some function between a to b. Now every point, even if it might possible function sometime positive and negative, I will take value at each point, and I will select maximum one. Okay, please be careful. One more important point I am going to share here. Suppose if you have just one dimensional function, okay, then notion of distance is given by absolute value. Okay, because absolute value will also satisfy the same kind of condition of the norm. Okay, so in one dimension, suppose that if you have to define the distance and point is lying here -5. So what is distance from 0 to -5? Anyone, could you please tell me quickly? What is distance from 0 to -5? -5.
5.
5. Why? Because I am taking the absolute value. So distance can be defined in one dimension by absolute value. And I have already told you that mathematicians are very intelligent person, or what they are doing, always they are telling that if you create hardware, simple hardware, then how to utilize that hardware to define operation, higher dimensional operation. Okay, so now you can see that you are able to observe everywhere, then using help of absolute value only, they are going to define some notion of norm everywhere. They are just going to use the notion of absolute value. So I have hardware program, I have software program. So software program is just telling us that how to calculate the component wise norm with help of hardware, and after that you are able to do after that you are able to calculate the norm. Okay, so here for simplicity I have taken only one dimensional function, so that is okay. But it might possible if you see LTI system, at that time AX is there and here X belongs to Rn. It means that AX belongs to Rn. Okay, at that time if you are going to calculate the norm of this function fx equal to AX, at that time you can see that I have some kind of no f1, f2 up to fn, that kind of things. Okay, so it might possible that whenever I have to define the norm, then I will see this function and after that I will see the maximum value. Okay, and whatever maximum value out of this at some time t, I will select that, and in that way I will define. Okay, so please check that all property will satisfy. So this is obvious because I have taken absolute value and maximum of that, and triangular inequality is obvious, and this is also obvious. So please check, this is straightforward. So in this way I can tell that initially I have norm linear space and I have defined norm linear initially I have linear space, vector space of continuous function, and how we have defined the operation. I have two operation, means pointwise addition and scalar multiplication, and top of that I have added this notion of norm, then this form a norm linear space. Anyone has confusion? So I have three different things I have to define in this space: pointwise addition, pointwise scalar multiplication, and after that norm using some kind of absolute value. Then this whole space, if that will satisfy all axioms of the vector space, then that is called non-linear space. So I am just adding one more notion. Okay, now let us come to the second example. Second example is also very much straightforward. You can see that I have any sequence. Suppose that I have some kind of, I am talking about a space of finitely non-zero sequence. Okay, so I have some kind of column vector, you can take. So in this column vector you can see that some element is non-negative or non-positive or non-zero, you can tell. And after that if I define like this, so again you know that if some vector is defined like this, then how to add two vectors. Okay, how to multiply that vector you are knowing, so that will form a linear space or vector space. Now if you will define the norm like this, okay, so what you can do, you can take the summation of all component, and after that whatever result that comes into picture, that I am going to define the norm. Okay, so here either you can define by two line or one line, that doesn't matter for us. So whenever we are defining norm, then we are defining like this. Okay, in absolute value, in order to distinguish between absolute value and norm, we are defining like this. But sometimes mathematicians are using both symbol. Okay, so whenever you want to use this kind of symbol for norm, then please write it that I am going to use this kind of symbol for norm, and now check all inequality will satisfy. Now in same space of continuous function, whatever I have just deal like this, and here I have defined norm like this. Okay, now I am going to define norm in different way. You can see here that now I am going to define norm like this, because I know that some quantity x, and suppose I have this kind of quantity. If I take the absolute value, you can see that now everything is become positive, and area is vector quantity, you know, because I am doing integral a to b, so this is positive quantity. Okay, again it is possible to show that all inequality will satisfy. It means that if a space is fixed, then it is possible to show that I can define norm in various way. And I am in last we are going to see that that way is infinity, means infinite many way I can define the notion of distance in some space, and based on our application or some physical interpretation I can choose that space. Okay, so in today's lecture, we due to that reason, that is very important. First point is that why different notion is required and how to choose it. Okay, if I some space is given and I have to do analysis of that space, then how to select that norm. So I am just also going to give that kind of example in today's lecture. Now another space, that is called the space of bounded, where function has some kind of bounded variation. Okay, so function is varying, but they are not going to infinity. Okay, and it is possible to show that I can define again that kind of a space, non-linear space on bounded function of bounded variation. Okay, so whenever we are talking about function of bounded variation, what basically we are doing nowadays, we are implementing everything with respect to computer and or digital platform, and you are well aware that digital things is never taking data continuously. They are taking data on the discrete point. Okay, and due to that reason, if you are going to enter something or going to see the behavior of function, that remains unchanged from these two interval, similar kind of things. Or if you are going to enter something, then our input is going to change after this interval only. Okay, and so we are going to define, suppose if something is given a b, so I have real number and subset of real number is called the interval. Okay, so this is the definition. So you have to remember that definition, that whenever interval is given, then whenever subset of real number is given, that is called interval. And interval may be closed, means both ind is included, both ind is not included, at least one ind is included. So I have several way to define the interval. Okay, so now what I am going to do, I have a to b, I am going to partition it into several interval, and after that, since we are talking about bounded variation, so what happens that if you see the ti instant or ti minus 1 instant, so meaning of boundedness we have defined like this. Okay, now total variation I am going to define like this. So total variation, if you see carefully, then that is also defined with respect to absolute value. Okay, another way, so I have already told you that that I have several way to define distance kind of notion. So total variation one can also define like this. Okay, and here please be careful, I have written supremum. So anyone has confusion in supremum or maximum, then please let me know. Okay, so just for the point of clarity, I am telling that suppose we have set like this, so could you please quickly tell that what is the supremum of this particular set? 5 6, Manali, Dhaval, anyone could you please tell? Nikhil, Subham, Amarjit, anyone, could you please tell me that what is difference between maxima and supremum? Okay, if I have set like this 5 to 6, could you please tell me that what is maximum value?
6.
You can see here I have open bracket, so 6 is not included. Okay, so what is maximum value? I
It is
cannot tell.
minus.
I cannot tell na, because 6 is not included.
Yes.
Due to that reason, uh, I cannot able to define maxima whenever this symbol is given. If this symbol means this point is included, obviously I can tell that 6 is maxima. Okay. Similar story is here. Minima I can define if 5 is included. If that is not included, then I have to way to tell that I don't know what is maximum of this particular set or particular interval, but there exists a supremum. Okay, and if I know the supremum, then all element is lesser than that. So 6 is not included inside this, but still that is supremum. Okay, so when maxima is defined, then supremum equal to maximum. Okay, in that way we are defining. Similarly, I have concept of infimum. So infimum and or infimum or supremum will give us the way when some maxima and minima is not defined, then how to deal with that situation. Anyone has confusion? That is very important concept, and frequently we are using inside the literature. So please be careful about that point. Okay, now
In inclusive case,
okay,
inclusive bracket case, supremum is 6.
supremum is exactly equal to maxima.
Max, no, sir. In not inclusive, exclusive case.
Okay,
That is
exclusive case. What's okay? 5 to 6. So like second
yes,
case. So
yes,
here
sir.
I cannot define the maxima because I don't know
Yes,
if someone is telling 5.99999 is maxima, then I will
yes, sir.
put 19. Okay, and whatever
Understood.
result, that is collapse, and due to that reason I cannot tell that I know the supremum, I know the maximum of this particular interval. So
Okay.
due to that,
What about supremum, sir?
supremum is 6.
6, no? Okay, sir. That's clear. Supremum is less or equal to maximum.
Yeah, yeah, yeah,
Okay.
yeah. It means that if maxima will not exist at that time, I have to some kind of way, and you can see that 6 is not included. So supremum may or may not included inside this set.
Okay.
Okay, that kind of result we have. Similar story about infimum. Infimum, you can see that 5 is not included inside this set, but still that is the infimum. But here, if I have close bracket, then infimum is 5 and minimum is also 5. So sometime max infimum or supremum is included inside set or not included inside this set. Okay, so this is one way to define the bounded variation. Another total variation, and another way is also like this. Okay, so continuously you can calculate the variation, and after you can do the summation. Okay, and total variation, okay, one can define using this way. So variation at the starting point and total variation, either you can take this way or this way. Okay, so in this way I can able to define the space with this kind of norm. Okay, so function of bounded variation with this kind of norm is called the norm bounded norm function of bounded variation. Okay, norm space with function of bounded variation. Okay, anyone has confusion? And again you can check that all properties satisfy, that is obvious. Now what happens, so far I am able to introduce the notion of distance. Okay, now with the notion of distance or notion of norm, I can able to define lot of concept inside the abstract algebra, linear algebra, or inside calculus also. Okay, so one such kind of concept that is very important whenever we are defining some kind of dynamical system. We have to understand that what is meaning of open set, what is meaning of closed set, what is meaning of the convergence, what is meaning of to tell that something is lie inside open set, something is not lie inside open set, and it is possible to show with help of the norm or norm space. I can able to define that kind of concept. Okay, so first important concept we are trying to understand, that is interior. Okay, so what we are telling, PB is subset of norm linear space. Okay, so what happens that I have some kind of vector space. Okay, and inside vector space what I am going to do, I am going to select some space that is called subspace, and I know that some norm is here. So I am going to select some kind of norm. So this subset now contains some norm. Okay. So what I am going to do, I am going to select P, and that is subset of norm linear space X. So this region I am going to select. Now you can see that here I have various point, infinite many point. Now suppose some point P belongs to this whole space P. So whatever subset I have selected, this is by capital P, and a small p is telling that element or vector inside this space with some proper norm. Okay, so we are telling that P is said to be interior point of P if there exists a epsilon, and such that vectors S satisfy x minus p less than equal to epsilon. So if you see this point carefully, we are just telling like this. Suppose I have to select this point P. So what I will do, I will now going to form some sphere around this. Why I am telling this as a sphere or ball? You try to see that ball is more commonly used. Now, whenever we are defining x x1 square and plus y1 square and equal to suppose 4 square. Okay, so what is notion for this? Have you understood my point? You have center x1 y1 and after that you have periphery x and y. Okay, and suppose radius is 2, so I can define like this. In coordinate geometry we have already learned. Okay, now suppose you are in three-dimensional space. This is a story about two-dimensional space. First you try to understand the story in one-dimensional space. In one-dimensional space, using absolute value, if I will tell mod x is less than p, then this point is p and minus p. So whatever this symbol, either you can take absolute value and or norm, that will represent this point from here to here. If you will write this kind of symbol, then that will represent this whole quantity, and if you apply less than equal to 0, then this is also covered. Similar kind of notion I can define for three-dimensional space, four-dimensional space, n-dimensional space. Okay, and shape, I am not caring about the shape, I am just giving the name ball. Okay, so whenever we are talking about interior point, so whenever we are defining some kind of norm, okay, because norm is telling that what is distance from x to p. What we found that in vector space, I have no way to define the distance between 2 points, and due to that reason I have introduced the norm. Now you can take any two quantity, I can able to define the distance between two quantity, because finally whatever quantity that converted, that comes into number, form of number, and we are telling that x and p, if that is 0, then x is exactly equal to p. In this way I am able to compare in higher quantity in higher dimensional space. So we are telling that x satisfy if this kind of condition for all member of P, then P is the interior of the subset P. So in this way I have defined the interior. So you can see that what is main theme. In order to define interior, I know I have to know this kind of notion. Okay, notion of norm. And P is subset of norm space. It means that I am just talking about some quantity which will follow the vector addition and scalar multiplication. If that will not follow, again I have to weigh, but I am not going to talk about that in this lecture. Okay, so I am assuming that in norm linear space we have to talk about interior point. So how to talk about interior point? You can define one norm. Norm will give you some way to define a ball, and I have infinite many norms, so infinite many way to define the ball. Okay, and if that will satisfy for all member of P, then that is called interior point. Okay, so basically whenever we are defining the interior point, obviously we are defining with help of a sphere which is centered at the x and radius equal to epsilon. So same kind of things I am telling. Anyone has confusion? Now, what is definition of open set? A set P is said to be open if P equal to interior of P. Okay, so due to that reason I am telling that entire space is open set. The unit sphere consisting of all vector x, and if that will satisfy this kind of relation, then that is called open set. So suppose that if you are writing x dot equal to ax plus bu and x belongs to Rn, we are talking about the open set. We are not talking about the some kind of closed set. Okay, we are telling that x can lie anywhere in a space, and at that time I can able to define some kind of ball. Okay, so you can take any subset, and at that time I can define the ball, and they will satisfy this kind of relation. That is the meaning. Anyone has confusion? Now let us come to the next definition. So whenever we are defining open, so obviously we are going to define the closedness. So closure, in our order to define the closed set, first I have to define the meaning of closure. Okay, so here you can see that whenever we are defining the open, at that time you can see that what I am telling, I have vector space, norm linear space, and I have subset of norm linear space, and I have selected some portion P, and I have selected some point P such that this relation will satisfy. Okay, for all epsilon greater than 0. Now here we are telling that a point x that belongs to x. So what you can do, now you can select any point. You have flexibility, and x may be non-linear space that is closer to a set P. Okay, so now what I am telling, I have some point, and now I am going to check that this point is closer to some set or not. Okay, here I am checking that some point inside the set or not. Here what I am telling, I have some point and I have some set. So I am going to see that that is closer to that set or not. So how to tell that is closer? If they will satisfy this kind of relation. Okay. So are you able to understand the difference between interior or closure? Anyone? If anyone has confusion, then please let me know. So if you see this relation, then this relation looks exactly the same, but interpretation is different. Okay, here I am telling that that point inside the some set or not. Here I am telling that I have some exterior point and I have some kind of set. So this point is closer to this point or not. And if suppose I have to tell that this is set and this is again set, these two set are closer or not. So I will check about all possible point. Okay, and after that I will see all point, and I have to check this kind of condition. If this condition is satisfied, then we are telling that that will satisfy the property of, or that is closure point of P. Okay, and that is denoted by P. Okay, so now a set P is said to be closed if that will satisfy this kind of property. Okay, anyone has confusion, then please let me know. Now another important thing, now we know the notion of interior, notion of closure. Another thing that is obvious from the norm linear space, that how to talk convergence in norm linear space. Okay, so uh, all of you are well aware that whenever I have one dimensional quantity, then I can talk about the limit of some point. How basically we are talking about limit. We see variation from left hand side, right hand side, and at this point we are seeing the variation, and in this way we are defining the limit. Okay, and we are tending the point because I know in which direction I have to tend wherever we are in one dimensional space. But wherever you are in higher dimensional space, now how to define limit in higher dimensional space, that is still not obvious, because you don't know in which direction you will move. Okay, so suppose that if this point is lying in three-dimensional space, so I don't know in which direction I will move. So only way I can construct some ball or some kind of structure, and I will decrease the radius of this ball. Anyone has confusion? So what I am going to tell now, that in higher order generalization of simple limit, whatever we have learned during our school time, now I have to construct some kind of ball. Okay, and if limit exists, then for every epsilon greater than 0, there exists a some number n. Okay, some number, some natural number n, such that I can able to give guarantee that x minus xn is the limit. And now could you please tell me that how to define distance in higher dimensional space? Which kind of operator is required? Anyone, could you please tell me? Any, quickly please tell me. Is it possible to tell that in higher dimensional space I can define distance by norm? So that should be less than epsilon for all n greater than equal to n. In this way, I can able to generalize the notion of limit in higher dimensional space. Anyone has confusion? Then please let me know. Because in one dimensional space, it is pretty clear that I can move in this direction, but in higher dimensional space, I don't know how to move. And due to that reason, I have constructed one ball. And how to construct ball? With help of any norm. You can take any norm, that doesn't matter, just that should be satisfy all three property. And after that, you have to check that for all epsilon greater than 0, there exists a natural a integer n, such that this quantity is less than epsilon for n greater than equal to n. It means that after this number, whatever point that comes into picture, that is going to lie inside the this sphere only, a sphere or ball only. Okay, because whenever I will tell a sphere, then that is very specific case. Okay, and proof here, why we are telling That is obvious from here. Whenever I am telling that xn tending towards x, then norm of x is also tending towards this, because this kind of relation is obvious, because whenever I am writing xn mod x, you can see that I can add x here, subtract x here. Okay, so and after that again I will apply the inequality, triangular inequality, and finally I will get this condition. Similarly this condition. So whenever we are telling that xn tending towards x, norm x is also tending towards norm x, and due to that reason that is tending towards 0. So a sequence converge, its limit is unique. So if I have convergence sequence, then it is possible to show that limit is also so unique. So whenever you have to prove uniqueness, what you can do, you can assume that you have two different limit, and after that you can show that both limit is equal. Okay, so I am telling that xn has two different limit, x and y. Now I am going to see the distance between x and y. How to see the distance in higher dimensional space? Again I have to take the norm. Okay, and after that I have added xn and xn both hand side, and after that x minus y is tending towards 0, so there is no difference between x and y. Anyone has confusion? So now you can see that what is beauty of non-linear space. Non-linear space is telling at least that if I have some kind of a space where I have column vector, matrices, function, and I have a some specific way to do operation, and if some axioms is satisfied, then I can also talk about the convergence. Idea of limit I can able to talk. Okay, and due to that reason, non-linear space is very important to learn. Okay, because you have to make sure that whenever you have system, then if your input is going to converge to some point, then where output is going to converge. So that kind of relation you have to know, and you cannot able to tell if you don't know these kind of concept. Okay, now let us come to the next part. So next part, some more same kind of things I have written here, that whenever we are talking about the convergence, you can able to define convergence in terms of spheres or some kind of ball you can tell. Okay, so whenever we are telling the ball, so xn, some kind of sequence xn converge to x if and only if given epsilon, the sphere contain xn for all n greater than equal to number n. So same kind of things I have written, that for every epsilon greater than 0, there exists some natural number, some kind of integer n, such that I have, if I am able to prove that distance between these two is less than epsilon for all n greater than equal to n, then x is the limit, x has a limit, that is xn, or xn is sequence, so xn has a limit as x. So whenever we are writing sequence we are writing like this. So try to understand in terms simple way. Suppose I have some kind of system like xk. Okay, so I have taken some kind of discrete system. So k equal to 0, I have some sequence k equal to 0. Suppose that I know that I have alpha x0. Okay, so x0 is given. Now you can able to generate all sequence. X2 is nothing but alpha, and here alpha 1, so x1, and after that you can see that you are able to generate another sequence x equal to 0, and similarly you can able to generate xk and alpha k into x0, like that, like this. Okay, so now you have to make sure that if you have this kind of discrete time system, okay, then under what condition this system is stable? Could you please tell me, anyone, that when this xk is tending towards 0, if I have discrete time system?
Alpha less than 1.
Yeah, alpha less than 1. Okay, so exactly that is coming from here. Okay, because now I have just taken the scalar case. If I have vector case, then how to select alpha I don't know. So but if you know this kind of definition, then I can apply, and easily I am telling that whatever norm of this alpha, because at that time alpha might become some kind of vector. Okay, what kind of property that will satisfy such that I can able to give the guarantee that xk tending towards 0, and we are stating same kind of result in terms of eigenvalue. Okay, now we have just seen that what is definition of closed set. So closed set, whenever we have defined, at that time we are defined that closed set using the concept of closure. Another way, a set F is called closed if and only if every convergent sequence with element has a limit. So in this way also I can able to define the closed set. You can take any convergence sequence xn you can take, and if every sequence has a some kind of limit, then I am telling that that set has a closed set. So I am going to skip the proof. Okay. Now one another important point, what we have found, that I have some kind of vector space. Okay, now I want to see that if I will apply some kind of transformation, and after that obviously if I apply some kind of transformation I have another space. So suppose here I have a space x and I know this is vector space. Okay, now what I am going to do, I am going to create some kind of transformation such that whatever resultant space y, that is also vector space. Okay, so that kind of transformation I am going to search. Okay, and if I am able to search those kind of transformation, it is possible to show that there exists a linear transformation if you have vector space, and if you apply this transformation, and if that is linear in some sense, I will tell you in what sense, then whatever generated space that remains the linear. It means that now you can see that you have some kind of system. Now you can interpret system as a transformation, and you can apply the input, and you know I am going to select input from some kind of vector space. It means that I am going to allow those kind of input only which satisfy the property of vector space. Suppose that if you are going to give some kind of continuous signal, then you are going to understand the addition of continuous signal in pointwise manner, scaling by pointwise manner. Okay, that is the meaning. Now what I am going to do, I am telling that under what condition whatever output that is going to generate from this particular system, that again fall in some kind of vector space only. It means that again that will satisfy some kind of axioms or some kind of binary operation. And it is possible to show that if system is some kind of, or transformation is linear transformation, then that will satisfy this kind of property. Okay, so let us define, and after that you are able to understand that why whenever we are defining linear system, at that time we are using some kind of concept like linearity or superposition or homogeneity. Okay, so what I am telling, transformation x and y be the linear vector space, you can select x and y, and D is the subset of x. Now you can select any subset, that is D. A rule which associate every x of element y is said to be transformation of x from y in domain, and y corresponding to x under this. So same like this is same like the function. In function most of time what we are doing, I have one input one output x and that map to fy. Now we are generalizing this in higher dimension space, and after that we are assuming that whatever element I am taking, they have also certain kind of property. So transformation is simply a function defined on one vector space x and taking the value in another vector space y. Okay, and a special case of transformation is called functional. Okay, and what is beauty of functional, that they will map vector space into some kind of real number, and real number is positive. Okay, and whenever you are going to learn optimal control, at that time we are basically constructing the functional. Okay, so functional means that is mapping from Rn to R plus. Okay, so have you learned LQR controller in this course, modern control theory course, LQR linear quadratic regulator? Have you learned that? Anyone? In course of modern control theory, that is whatever portion that taught by Professor Sandeep Ghosh, means is he cover that portion, that linear quadratic regulator LQR?
No, sir.
Okay, don't worry. In next semester, one course is optimal control. At there we will cover. Okay. So actually, what happens? Always we are defining performance function, and you can see that comparison I can only do in one dimensional space. So even if some quantity lying in higher dimensional space, we have to define some way to map n dimensional space to one dimensional space. And at that time, functional is very much important. important. So whenever you are dealing with any optimization problem, at that time functional is required. Here please interpret this as a x power half. So a square root, I am assuming that a square root of some number is always positive. That kind of interpretation I have. So you can see that this function this way. So several way you can able to define the functional. Okay, now I have told you that there exists one very special class of transformation, okay, that will satisfy this kind of property, that if you will give some kind of input like the linear combination, okay, and if transformation is linear, then it is possible to show that that will satisfy this property. Okay, so could you please quickly tell me that LTV system or LTI system, linear time varying system, linear time invariant system with initial condition equal to 0, that will satisfy this property or not? Have you able to correlate the linearity with this, or whatever superposition you have additivity or homogeneity? Are you able to correlate like this?
Yes, sir.
And due to that reason, you can see that whenever I have linear system, then there is no need to worry about the space. Why? Because if I will apply some quantity from vector space, again that will satisfy the all property of vector space. Okay, and you can see that whenever we are solving LTI or LTV equation, so suppose if I have some system like AT into XT and plus BT into UT, at that time if you see the solution carefully, then I am writing solution into phi some state transition matrix T0 and XT0, and after that T0 to T and phi T tau u tau into d tau, like b u tau into d tau, like that I am writing. So if you can take initial condition equal to 0, then you can see that this is also a linear operator. So please check it, this property will satisfy or not. So it is pretty easy to check. Okay, now what happens that whenever we are talking about the linear transformation, we are just talking that how one space, linear vector space, map to another vector space. So same kind of things I have written here. Now what I am going to do, I am going to introduce one more notion inside this mapping, and it is possible to define, it is possible to, after adding that notion, it is possible to define the continuity. Okay, so now what I am telling that since I am going to map to a space, so I have some system, I will give input y, and after that I am going to look towards fy. Okay, so I am telling that a transformation T, so T may be linear or not be linear. Okay, so suppose I have some kind of transformation T mapping a norm linear x into a norm linear y. So if this transformation, okay, is continuous at x equal to x if for every epsilon there exists a delta such that this condition will satisfy. Okay, so in this way, using the help of the notion of norm, again I will define the continuity. Okay, so basic idea, if you see the continuity, how basically we are defining the continuity. Suppose I have some function fx, okay, and I have to check that this function is continuous or not. Okay, so how to check? First you can plot the graph, okay, and after that project this graph on y-axis fy and zoom it. Okay, and after zooming you try to see that where is your the domain, and after zooming it, if this is finite zoom and if this remains the finite, then we are telling that function is continuous here. Okay, so suppose I have one dimensional quantity, then we are telling that for every epsilon greater than 0 there exists a delta that is function of epsilon, because I have whenever I am zooming the y-axis, corresponding zoom is appear here. So now you can perform any amount of zoom. Now you can see that epsilon is related to the fy, and due to that reason I am writing fx, and suppose f0 I want to zoom around 0, so I will take the absolute value, and after that that I am telling that if you will do this kind of zoom, then whatever zoom is appear here, so at that time x minus x0 is less than delta, that is epsilon. And due to that reason, whenever we are defining for every epsilon there exists a delta. So if you start from this zooming, then whatever output that remains in that way we are defining basically. And same kind of things now in higher dimensional space, you can see that I have just replaced by the absolute value by node, and in this way I can able to define continuity in higher dimensional space. So a transformation T mapping a norm space X to norm space Y is continuous at the point x0 x belongs to X. If X tending towards x0, then you have to make sure that Tx and tending toward Tx0. And if this, I am talking about continuity at one point, but if you are able to check in whole space and this condition is satisfied, then we are telling that T is continuous. In that way we are defining. And continuity is very much related to the stability. Okay, in next class I will tell you about that story. Now what happens, I will just take 5 more minutes and after that conclude the today's lecture. So what I am going to see now, suppose I have some kind of sequence of a scalar zeta 1 zeta 2 up to zeta n, okay, or zeta infinity you can take. Okay, now I have a space where I am defining each element in form of sequence. Okay, so could you please verify that that is vector space or not? Quickly, could you please tell me that that is vector space or not? Suppose I have sequence like zeta 1, zeta 2, zeta n. Okay, so is that form a vector space? So addition of two converging sequence, what happens? That is converging or not? Anyone? Still converging, and due to that reason I can the form the vector space. Now you can see that I can able to define norm in different way. So same sequence, space remains the same, and I can define norm. Absolute value I will take power p and 1 by p, and p is like from 1 to infinity. So infinite many way I can define norm on the same space. That message I am going to transmit from the here. Okay. So now suppose that if you have column vector x1 up to xn. Okay. So now if you have x1 up to xn, so Dhawal, could you please tell me that how to define the one norm by seeing that formula of xp? Dhawal, Dhawal, are you here?
Yes, yes, sir.
So could you please tell me, suppose that if you have x1, x2, xn, then how to define the one norm? I will give you hint. Okay, what you can do, in place of p you can substitute 1. So this become zeta I or p equal to 1 power 1 by 1. So that is summation of absolute. So how do you think how to define? Now this is truncated to n because I have just considered column vector which has n entry. So could you please tell me that what is value of this
Zeta 1 plus zeta 2 plus up to zeta n.
summation I equal to 1 to n and absolute? Is it correct?
Yes, sir.
And this norm is called one norm. Okay, similarly what you can do now, you have to calculate infinite norm, suppose. So in order to calculate infinite norm you have to substitute like this. So each quantity you have to select and see whatever the supremum value or maximum value is exactly equal here. And due to that reason, if you are going to calculate the infinity norm for this, then that is nothing but xi, and you have to just see the max over I, all I. Okay, in this way, in whole one space I can define norm in different way. Okay, so in next class I will also tell that if you have matrices, then how to define the norm, because whenever we are talking about bonded input bonded output, then that kind of concept is required. So I know that lecture is going to over from today onward. Today is the last class, but I will take some more classes. Okay, and probably I will take class on Saturday and Sunday, or I will send some recording also. Okay, so and syllabus of the end same is based on whatever lecture I have covered from my portion I am telling, and whatever whatever video recording I am going to send you. So I will send you video recording up to 16 I will send you more 4 or 5 more lecture I will send. Okay, I will take 1 and 2 lecture, and after that I will not send more. I will send just 1 and 2, and please go through that also. And examination is based on whatever class I have covered, and 2 and 3 more lecture recorded lecture I am going to send, and based on that one. Okay. Now, if you have any question from non-linear space, then please let me know. Anyone? So let us conclude the today's lecture. So what happens that what kind of things basically I have actually discussed in the today's lecture, that I have normally I have some kind of linear space or vector space, but there is no notion of distance. So how to add the notion of distance such that I can able to talk about the convergence, I can talk about the continuity. Okay, I can able to define some kind of notion of distance in different way, that also we are able to see using the today's lecture. And notion of distance in any vector space may be infinity. Okay, we have seen a last example where a space I have taken the sequence of the scalar, and after that I have defined some kind of p naught. P could be anything from 1 to infinity. So with this remark, class is going to end from my side. So if you have any question, then please let me know. Any question, any confusion?